Keep the heading as a basic classification of signals. Basic classification of signals. So what are we going to do in the basic classification? In the basic classification, without knowing about the characteristic of a signal, we are going to classify the signals. It is something like having the different students across the world. We are trying to classify them based on the country to which they belong. Okay, we are not looking into the characteristics, whether the person is good or bad, what are the professions of that particular, what are the streams of students. We are not looking into it. We are just looking into, okay, the superficial part of it, which is nothing but the way in which the signal is going to look, the way by which the signal is going to look. So without studying characteristics, just a broad classification that we are going to do is nothing but a basic signal classification, in which we are going to classify the signals as number 1, continuous time and discrete time signals. Number 2, analog and digital signals. Number 3 is real and complex valued signals. And number 4 is deterministic and random signal. Right? So we are going to have 4 different classifications: continuous time, discrete time signals, analog and digital, third is real and complex valued signals, and fourth is deterministic and random signals. You can please note it down, the basic classification. Here we are not looking into the characteristics like whether the signal is periodic or not, whether the signal is causal or not, whether the signal is bounded or not. We are not at all looking into the characteristics of it. It is just by the way in which the signal is going to look, we are going to have a different classifications: continuous time, discrete time, analog, digital, complex, real, deterministic and random. Right, so first thing we are going to discuss it is continuous time and discrete time signals. Continuous time and discrete time signals. So what is continuous time and what is discrete time? Can anyone comment on this? What is a continuous time signal and what is a discrete time signal? Let us say that we are having a signal which is varying with respect to time. Let me indicate my time with t, and the signal, let me represent it as a function of time. The signal is a function of time. Now you can see that at each and every instant, there are infinite number of instants we are having. So but for each and every instant, the signal value is present. That sort of signal is what we call as a continuous time signal. So continuous time signal is that particular signal where the signal is defined for each and every instant of time. Every instant of time. This is what we call as a continuous time signal. If the signal is defined for each and every instant of time, then we say the signal is going to be a continuous time signal. A continuous time signal. Now, the other type of signal that we can have is something like this. Let us say 1, 2, 3, 4, 5, 6. And let me represent the time with n here, and the amplitude, let me say it is f of n. Now here what you can see is that the values of the signal is present only for some finite instants, only for some discrete instants of time, only for some discrete instants of time, the signal value is defined only for some discrete instance of time, the signal value is defined. This is what we call as a discrete time signal. Discrete time signal is defined only for discrete instance of time. Signal is defined only for discrete instance of time. This is what we call as a discrete time signal. Discrete time signal. Right? So here we are not at all discussing about the nature of the amplitude. It can be anything. But what we are focusing here is about whether we have the signal value available for each and every instant, or it is available only for some discrete instance of time, based on which we are classifying the signals as a continuous time signal and a discrete time signal. Okay? So as a representation of a continuous time signal, we always represent the continuous time signals independent variable with t, where small t is indicating the time and the signal is represented by the function of time. Whether we can write f of t, x of t, y of t, whatever it is just the function of time. Okay, so we have a representation like this: f of t or x of t or y of t. And what is the nature of t here? T is the time. The time can only be a real value. So any real value of time, the t nature is going to be real. Whereas when it comes to the top, the discrete time signal, the representation of a discrete time signal is that the time is represented by n, where the nature of n is going to be an integer. The nature of n is going to be an integer. Right? The value of n is going to be 1, 2, 3, 4, 5, 6 and so on. The nature of n is going to be an integer. And the values that you're going to have can be anything. We are not at all discussing about the amplitude. But the representation of a signal will be something like f square brackets, or we can say it is a closed brackets of n. Or we can write x of n, or we can write y of n. Right? So here we are having the open brackets, whereas here we are having the closed brackets. Here the independent variable is n, where n is an integer, whereas here the independent variable is t, where t is a real number. In both the cases, whether it is n or it is t, in both the cases we are talking about time only. Okay? And whereas here the signal is varying with respect to time. So the continuous time signal is something where the signal or the amplitude is defined for each and every instant of time. Okay, the other classification we are having is that the discrete time signal, where the signal is defined only for some discrete or finite instance of time. Okay, so this is the classification we are having: continuous time signal and discrete time signal. So this is how the representation of a continuous time signal is, and this is how the representation of the discrete time signal is. So any physical examples? Yes, so you can consider the speech that I am delivering. The speech that I am delivering, if you see the amplitude of the speech that I am delivering with respect to time, you can observe that for each and every instant of time, you will be observing the amplitude. You will be having a wave pattern which is something like this. So these are the instants where I am shouting. Right? So this is nothing but an example of a continuous time signal. So the speech signal that I am having is an example of a continuous time signal. Right? So speech signal that I am having is nothing but an example of a continuous time signal. So the waveform sinusoidal variation, the sinusoidal variation you're having is also an example of a continuous time signal. Now what is the example of a discrete time signal? See, there can be many examples of discrete time signal, but to simply understand, if I want to represent the crime rate of India, let us say this is 2004, 2005, 2006 and so on. The crime rate of India. So this is nothing but a discrete time function. This is nothing but naturally discrete time signal, because I am having the finite instance for which my value is defined. This is what we call as a discrete time signal. In fact, the weightage slide that I have shown, you might have seen the weightage slide that I have shown, where I have shown the weightage for different years and the marks that we are having. Here the signal is nothing but the marks, whereas the time is nothing but the year, the corresponding year. It is also an example of a discrete time signal. Right. So another example I wanted to give regarding continuous time discrete time is that, for example, if I give you a task of measuring the temperature of a room, okay? So if I give you a task of measuring the temperature of a particular room, and if I give an instrument which can measure, for example, our classes starting at 6 and ending at 9. So what you are doing is that throughout the time period of the class duration, you are trying to measure, and the instrument supports that it gives you the temperature for each and every instant of time. The temperature is measured for each and every instant of time. Then this is going to be a continuous time signal. Whereas if I give you such an instrument which will give you a response for every half an hour, let us say at 6 o'clock, again at 6:30, again at 7 o'clock, 7:30, so you are getting just a discrete value of information for every half an hour, then it means that it is nothing but a discrete time signal. Is it clear to all of you? So that is the difference. If you are able to get for each and every instant, then we call it as a continuous time signal. But if you are getting only for some discrete instance or some finite instance, then we call it as a discrete time signal. Now, you know, these days, whether you are talking about computers, whether you are talking about calculators, all the instruments or all the devices that you are having are actually discrete time. If you see the memory that we are having, it is nothing but what? It's nothing but a discrete memory. Whether it's a laptop, whatever memories that we are having, pen drives, these are all discrete memories. So they will be storing it in the form of the samples. And there are so many advantages of having the information in the discrete nature. One of them is easy to store. Okay, if I wanted to store all the information, then I will be having so many number of data, so much amount of data. And there are so many advantages, like if you are having a discrete information, it will be more immune to noise. And there are so many other advantages because of which we actually recommend these days to have a discrete signals. The best example is that whenever you are downloading any song, when you try to download any particular song, then there it will be mentioned you can download from 64 kps, you can download from 128 kps, you can download from 320 kps. Have you seen this? Whenever you are trying to download any particular song, what is the kps? kps is nothing but kilo samples per second. It means that If I say 24 kps, it means that in a second you will be having 24,000 samples of data. Okay, so that is also a discrete information because you have already sampled it. So one way to convert a continuous time signal to a discrete time signal, this process is what we call as a sampling. This process is what we call as a sampling. The conversion from continuous time to discrete time. See, any signal which is continuous in nature can be converted to a discrete time when it passes through the process of sampling. When you are able to sample the signal, then continuous time can be converted into a discrete time signal. Can be converted into a discrete time signal. Yes or no? For example, if I am having continuous time signal, if I take the samples of it, let us say I am taking the different samples from here. So instead of taking all the information, I am only just taking the samples of it. Now it is becoming a discrete time signal. So how to convert a discrete time to continuous time? We generally use the concept of low pass filter. And there is something called as a reconstruction filter which we use. Of course, we will be discussing about that when we discuss about the concept of sampling. Right? So as of now, we are just discussing about the nature of the signals that we are going to have. One is a continuous time, the other is a discrete time, and the process by which we can convert a continuous time signal to a discrete time signal. So let us consider that we are having an information which is something like this. Now when you have sampled, it means in a way we are trying to chop the signal. Okay, we are trying to chop the signal. And we are considering only some instants. We are only considering some instants for which the information is available. Now, when you are doing that, then when you are cutting it, you are going to cut it with a sampling interval. Let us say that here the signal is actually starting from 0, and after that you are going to have a sample, let us say at a time called as Ts. And the next sample that you are going to have will come at 2 Ts, whereas the next sample will come at 3 Ts, the next sample will come at 4 Ts, and so on. It means for each and every interval of Ts, you are going to have a sample. That is what we call as a sampling interval. It means that the duration after which you are going to have a next sample is what we are calling as a sampling interval. And you can see sampling interval is the space between two consecutive samples. If you take any two successive samples, consecutive samples, then the space between them is also Ts. Correct or not? Okay, so a signal which was something like x of t before, because initially the signal was what? A continuous time signal. Initially the signal was a continuous time signal. Now, after sampling, what it has become? After sampling, now you don't have this information, isn't it? Now you are not going to have this information. You will only have the samples. It means that now it is a function of nTs. It is going to be nTs. Why? 0 at 1 Ts, 2 Ts, 3 Ts, 4 Ts, 5 Ts, 6 Ts, and so on. So I am writing it as x of nTs, where n is something which is changing and Ts is present everywhere. So we are calling it as a x of nTs. Okay, so the result after sampling is what we call as a x of nTs. The simple thing is here is that when you do the sampling, you are replacing your t with that of nTs. Okay, so this particular signal we can also call it as x of n. Because Ts is going to be a constant. This Ts is going to be a constant. So because it's a constant, we will not consider here it is. So we are writing it as x of n. Okay. So to solve a particular problem, like converting a signal from continuous time to discrete time, what we are going to do is that we are just going to consider that t is equal to nts. We are just going to consider that t is equal to nts. For example, in this problem, we are given a signal which is x of t. Now, what is x of t? X of t is nothing but cos 2 pi t. X of t is nothing but cos 2 pi t. Now when you are sampling at some frequency, what we will see what is the sampling frequency. Once it is sampled, we are going to replace the t with the of nts. Once it is sampled, then we are going to replace t with the of nts as we have discussed here. Okay, now x of nts, which is a sampled signal, will be cos of 2 pi nts. Cos of 2 pi nts. Now what is the relation between sampling interval and sampling frequency? What is the relation between sampling interval and sampling frequency? We know that relation between the of time period and frequency. That whenever you know the time period, the inverse of the time period is nothing but the frequency. Whenever we know the time period, the inverse of the time period is nothing but the frequency. So the sampling frequency is the inverse of the sampling interval. The sampling frequency is the inverse of the sampling interval. For example, if I say that I am having one sample for every millisecond, I am having for every millisecond I am having a single sample. Then in 1 second, how many samples are we going to have? If I am having a single sample for each and every millisecond, then for 1 second, how many samples are we going to have? So we are going to have 1000 samples. Correct? If for 1 millisecond you are going to have a single sample, then for 1 second we are going to have total 1000 samples. It means that sampling frequency is nothing but how many number of samples you are going to have in a single second. How many number of samples we are going to have in a single second is what we call as a sampling frequency. Right? So which is nothing but, let us say this is Ts. Okay, sampling interval is nothing but Ts. Then 1 by Ts is nothing but 1 by 1 millisecond, which we call as a 1000. Okay, so this is what we call as a sampling frequency. This is what we call as a sampling frequency. So which is equal to 1000. And what is the unit? The unit either is going to be heads or per second. If I am having 1000, I can write it as 1000 heads or 1 kilohertz, or I can write it as 1000 samples per second, 1000 samples per second, or I can say 1 kilo samples per second, or I can say that I am having 1 kilo samples per second. And whatever classification of continuous time and discrete time we are having is important because of the fact that from now onwards, whatever we are going to learn, we are going to learn it as continuous time signals and discrete time signals. We will be seeing the standard signals like impulse, step, ramp in the case of continuous time first, and then we will go into the again impulse, step, ramp in the case of discrete time. Okay, so our approach will be something like this, that we will be learning for continuous time signals, we will also be learning for discrete time signals. And same again we will be seeing for continuous time signals, continuous time systems and discrete time systems. We will be having something called as continuous time Fourier analysis and discrete time Fourier analysis. So this particular classification that we are seeing between the of continuous time and discrete time is important. Right, so I think we have understood about what is a continuous time signal and a discrete time signal. Next thing that we are going to discuss here is the analog signal and a digital signal. The second classification that we are going to see here is analog signal and a digital signal. So what is an analog signal? See, I think when we discussed about a continuous time signal and discrete time signal, something that we are focused on is that the time, right? So if the signal is available for each and every instant of time, then we call it as a continuous time signal. If it is available only for some discrete instant of time, then we call it as a digital signal. Now when we talk about analog signal, whatever treatment that we had for time axis, if I do the same treatment for the signal axis, if I have the same treatment for the signal axis, actually if I have, for example, if my time is 0 to 5 seconds and my signal is available for each and every value of t, can you please tell me between 0 and 5 how many values are present between 0 and 5? I am only talking about time as of now. How many values are present between 0 and 5? Okay, infinite. Can you please tell me how many values are present between 0 and 0.1? How many values are present between 0 and 0.1? There are still infinite number of samples which are present between the of 0 and 0.1. Yes or no? Okay, so when we considered continuous, it means that there are infinite set of values that are available in a particular range. If I break it and if I say that no, now you are not going to have that, now you are going to have only like 0, 0.5, 1, 1.5, so on till 5. Now what you are trying to do is that you are trying to discretize the time. You are trying to discretize the time. The same if I do with the amplitude. Initially if I say from 0 volts to 5 volts, in the range of 0 to 5 volts, if I know that my signal is present only between 0 and 5 volts, it is varying between 0 and 5 volts. It means that the signal can take any value of amplitude. The signal can take any value of amplitude between 0 and 5. Yes or no? It can take any value of amplitude between 0 and 5. Correct or not? This is what we call as an analog signal. This is what we call as an analog signal. If the amplitude of the signal can be any value, then we call it as an analog signal. It means that each and every value of amplitude is defined. For the signal, if each and every value of amplitude is defined, then we call it as an analog signal. In other way, if the amplitude is continuous, then we call the signal as an analog signal. Okay? If the amplitude is discrete, then we call it as a digital signal. Just like the way that we have done a treatment for the time, that if each and every value of time is allowed, then we call it as a continuous time signal. If only some finite values are allowed, then we call it as a discrete time signal. In the same way, if I do with the amplitude, that if each and every value of amplitude is allowed, then I call it as an analog signal. If only some finite values of amplitudes are allowed, then I call it as a digital signal. Okay? Yes, I'll come to that particular point that students are saying that if time and amplitude both are continuous, then we call it as an analog. I'll come to that particular point. Is it clear? So as of now, we are only talking about the amplitude. We are not at all talking about the time. Okay? So if we are talking about the amplitude, if each and every value of the amplitude is available, then we call it as an analog signal. If only some discrete values of amplitudes are available, then we call it as a digital signal. Okay? So this particular process, just like the way the process of converting a continuous time signal to a discrete time signal is what we call the process of converting a continuous time signal to a discrete time signal. What did we call it as? We called the process as a sampling, isn't it? We called the process as sampling. Similarly, if I wanted to convert an analog signal to a digital signal, this process is what we call as a quantization. See, in our subject of signals and systems, we are never concerned about whether a signal is going to be analog or digital. Never. We are never going to be concerned about whether a signal is going to be analog or digital. because majority of the treatment that we're going to have is between the of continuous time and discrete time. We'll not talk about analog and digital, but if at all we talk about analog and digital, if you try to convert an analog signal to a digital signal, then the process is what we call as a quantization process. It's what we call as a quantization process. Okay, so how are we going to do the quantization? I'll just show you an example. Just let me add one more thing, that whatever things that we are discussing in today's class is not important in the examination point of view, is only for your knowledge. Okay, all the things. Okay, no one is going to ask you what is an analog signal, what is a digital signal, what is continuous time signal and discrete time signal, what is real signal, complex signal. They will just be using this terminology. I'm having a continuous time signal with frequency so and so. I'm having a discrete time signal with a frequency so and so. So to just understand with clarity the terminology that we are having, that's why I'm explaining this particular concept. But having said this, anyone can ask the question, what is an analog signal and digital signal in your interviews? For sure the question can be asked depending upon, based on whether it's an analog, continuous time signal, discrete time signal, digital signal, real signal, deterministic signal. All these things can be asked in your interviews, but never these are going to be specifically asked in your GATE examination, right? So I'll just explain you slightly about the concept of quantization. If you are an easy student, electronics and communication, you will learn this particular concept of quantization elaborately in the subject of communication systems. Okay, for the remaining streams, okay, in fact communication systems is also there in the case of instrumentation. For electrical students it's not important, but just for understanding point of view, I'll just tell you how the quantization happens. Let us say that my signal value is changing between the of 0 and 5. Okay, so what I'll do is that I will be taking only the parts of 0, 1, 2, 3, 4 and 5. Okay, so I can either have the value of 1, 0, 2, 3, 4 and 5. No other value I'm going to have. What I'll do is that I will be keeping some levels in the middle. 0.5, 1.5, 2.5, 3.5. Okay, so these are nothing but the other levels that I'm going to discuss, but the signal is only going to have these integers. These are what we are calling it as the mid levels. Now, if the level is less than 0.5, whatever level of the signal, for example, if I am encountering something called as 0.4 as the value of the signal, I will be rounding it off to 0. I will be rounding it off to 0. So any value that falls between the of 0 and 0.5 will be rounded off to 0. Any value between the of 0.5 and 1.5, any value between the of 0.5 and 1.5 will now be rounded off to 1. Any value between the of 1.5 and 2.5 will be rounded off to 2. Any value between 2.5 to 3.5 will be rounded off to 3. And this is how we do the quantization. This particular process of rounding off, is what we call as a quantization. This particular process of rounding off is what we call as a quantization. Is it clear to all of you? Okay, so by the process of quantization, we try to convert. Initially, what is there? Between 0 to 5, each and every value of the amplitude is available. But after doing quantization, only 5 levels are available. 6 levels are available. 0, 1, 2, 3, 4, 5. Right? Totally 6 levels are available. This is happening because of the process of quantization. Right? So now, we know that a process of converting an analog signal to a digital signal. Okay, so initially what we are having? We are having a signal which is continuous in amplitude and continuous in time. Initially we will be having a signal which is continuous in amplitude and continuous in time. The first thing that we are going to do is that we try to convert the signal from continuous time to discrete time. And what is the process that we are going to follow? If I am having a signal which is continuous amplitude and continuous time, the first process that I'm going to follow is to convert a signal from continuous amplitude to, continuous time to discrete time. Am I touching the amplitude? I am not at all touching the amplitude. And this process, as you know, we call it as a sampling process. Right? And then we convert a signal from continuous amplitude to a discrete amplitude. We convert a signal from continuous amplitude to a discrete amplitude. Already the time was discretized. So this is what we call as a quantization. Quantization. Now if you see, we have started with a signal which is both continuous amplitude and continuous time. And then first of all we have implemented, this is the general norm that we follow. That we first try to sample and then we try to quantize. Okay. So initially you had a continuous amplitude and continuous time signal. Here we had a continuous amplitude and discrete time signal. Here you had discrete amplitude and discrete time signal. So here the nature of the signal is analog. Here the nature of the signal is analog. Can you please tell me here whether it is analog or digital? Whereas here it is digital. Okay, so the process of converting an analog to digital, it will generally go through converting continuous amplitude to continuous time to discrete amplitude and discrete time. That is why sometimes generally we call analog signal is something which is having continuous time and continuous amplitude and continuous time, whereas digital signal is something which is having discrete amplitude and discrete time. This is the general expression, general representation. Generally, analog signal is something which is having continuous amplitude and continuous time, whereas digital signal is having continuous amplitude, digital amplitude and discrete time. Okay, so this is the general norm that we follow, but specifically if anyone asks, then analog simply means continuous amplitude, nothing to do with time, and digital means discrete amplitude, nothing to do with time. This is the true meaning of analog and digital, whereas in a general meaning we say analog is something which is having continuous amplitude and continuous time. Why? Because of the simple reason that all our physical signals are something like this. All the physical signals that we are, for example, whatever I'm talking is something is going to have the values of amplitude which are continuous in nature and the values of time which are continuous in nature. So both of them, so physically uttered signals are generally going to be analog signals. So when you are using your technology, so that you are having a digital signal. And having a digital signal will have a lot of advantages. So in a general perspective, if anyone says analog, it can infer that it is both continuous amplitude and continuous time. And in a general perspective, if anyone says what is a digital, it can be discrete amplitude and discrete time. But specifically, technically speaking, analog means continuous amplitude and digital means discrete amplitude. See, encoder is something that we generally use after quantization. After quantization, we use something called as encoder. So encoder is something which converts the values like 1, 2, 3, 4, 5 into something like 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. This process is what we call as encoding. We give a specific code for each and every value of amplitude that we call as a encoding. And of course, after encoding also we are having a digital signal. And digital signal, generally what we have understood is that digital signal is generally in terms of zeros and ones. Okay, that is after encoding. After encoding, it will be in the form of zeros and ones. It doesn't mean that if it is not in the form of zeros and ones, it is not a digital signal. It is wrong. What is the difference between discrete, digital, analog, continuous? So it's a good question. See, continuous and discrete, these are opposite. Continuous and discrete are opposite. You might have seen in mathematics also, we have discussed about something called as a continuous random variable and a discrete random variable. Do you remember? Continuous random variable and discrete random variable. Those who haven't attended, it's okay. So what the meaning of saying the continuous is that you are having each and every value. Each and every value, then we call it as continuous. If only specific values, then it is a discrete. So just continuous and discrete is just having this particular meaning. Okay, so when I talk about continuous, just if I am saying continuous signal, then what I mean is that both amplitude and time are continuous. Just continuous signal. Because for a signal, both amplitude and time are important. Both amplitude and time are important. So if I say it's a continuous signal, then I mean that both amplitude and time are continuous. If I say it's a discrete signal, then I mean that both the amplitude and time are discrete. Okay, rather if I say analog signal and a digital signal, analog means that I am talking specifically about the amplitude. Digital signal, if I am specifically talking about the amplitude, which is discrete in nature. Okay, so if the amplitude is continuous in nature, I call it as an analog signal. If the amplitude is discrete in nature, I call it as a digital signal. See, we'll come to the real, complex and deterministic and random in the next class.